So we're starting in chapter 10 now, and chapter 10 is going to be on sequences and series. So first off, we have to describe what a sequence is, because we're going to build that into what a series is and go from there. A sequence is going to be a set of things arranged in order. It's a set that's got order to it. It's a list of numbers, essentially, where each number is given a space in line, so to speak, and each of those numbers will be called a term. So we're going to be using that word a lot, calling things terms. And so a list of terms in order make up a sequence. If for every positive integer n, which is the natural numbers, just 1, 2, 3, 4, and so on, there's associated a real or complex number a sub n. And so we have a sub 1, a sub 2, a sub 3, and so on. That's our infinite sequence. And so that gives us our mathematical definition of a sequence. A sequence is a function defined to be from the natural numbers to the real numbers. So this is the domain, and this is the codomain, or where the range lives. So any function that goes from the natural numbers to the real numbers is a sequence. So every natural number we plug in is going to have some sort of sequence term, and so our natural numbers are 1, 2, 3, 4, and so on, all the way up. So important things to note is that since each of these has an order, we can talk about the first term a sub 1, the second term a sub 2, and the nth term a sub n. Every term has a successor, so when we start talking about our general a sub n, we can talk about a sub n plus 1. And this goes on forever. There is no last term. This is an infinite sequence. And as it says here, the most common thing that we can do is give a rule or formula for the nth term. So if we have 1 over n as our nth term, then we've got 1, 1/2, 1/3, 1/4, 1/5, and we would keep going on forever. As it says here, sometimes 2 or more formulas may be employed. And so we've got 2 different formulas, and we have to kind of figure out where do these fit in. We need to figure out where is a sub 1. Does it belong to this guy or this guy? And so we note what these subscripts mean here. Think about 2n. If we plug in different n values, starting with 1, we get 2, 4, 6, 8, and so on. If we look at 2n minus 1 and we plug in n equals 1, we get 1, 3, 5, and so on as well. So this is a very common trick. Having 2n minus 1 will give us odd numbers. Having 2n will give us even numbers. And so our an will come from this first one. We'll plug in 1, and we get a sub 1 equals 1. For our second term, we want a sub 2. And to get that, we'll have to plug in 1 for n into this second formula. That gives us a sub 2 equals 2 times 1 squared, which is 2. A sub 3, we would go back to the odds. We got 1 there. A sub 4, we get by plugging 2 in for n. So we plug 2 in here as well. 2 squared is 4 times 2 is 8. We go back to the odd terms, we get 1 again. And so for a sub 6, we plug in 3 for n. So we plug in 3 here. 3 squared is 9 times 2 is 18. So that would be the first 6 terms of this. And so we would keep switching back and forth. Always 1s for the odd terms. For the even terms, we plug in higher and higher numbers for n. So these are known as explicit formulas. There is some n you plug in and you get whatever term out. Another example of defining a sequence is carrying on after a given start. So this is going to be, we have the first 2 terms defined, a sub 1 and a sub 2 are both 1. After that, we define the next term based off of the previous terms. So this is going to be an implicit definition. The next term purely depends on what comes before it. There are sometimes ways of expressing these guys as explicit terms. This is often really difficult. So for instance, the Fibonacci sequence here, we'll figure out the first 6 terms. We've got a sub 1 and a sub 2 are both 1. And then we've got a sub 1 and a sub 2. We're figuring out a sub 3. So n equals 2. So a sub 3 would be equal to a sub 2 plus a sub 1. It means we add the previous two terms together. Then we add the previous two terms together. And then we add the previous two terms together. And again, and again, and again. The explicit formula involves actually a bunch of irrational numbers. In fact, radical 5 is a big player in there. It uses phi, which has to do with the golden ratio, and it's a rather complicated formula. So we're not really going to be dealing too much with that conversion process. So, like we said, the essential thing for a sequence is that we have a function defined on the positive integers, so that f of n is the nth term of the sequence. So that's what we got here. Our function defined on the positive integers going to, in some cases, are real numbers. In some cases, we can actually have the complex numbers here. We're not going to be dealing with that. We're just going to be dealing with the real numbers. But that's what we have. So a couple ways that we can sort of group these guys together in symbols. We have, first off, sort of just listing in the typical set notation, listing all of the different terms that we have. We like to be able to have the general term, if possible, listed somewhere in our list. As you can see in pretty much all of these, we have that general term somewhere. We do like having a sub n in an explicit formula if at all possible. So another thing we could do is sort of have a singleton here, a single object in our set, but it's a sub n. We can declare where n starts and stops. In this case, it doesn't stop, it goes on to infinity. And since it goes on to infinity, and this is a very standard sequence then, going from 1 to infinity, we can just put a set where a sub n is the only object in there. That subscript n is the index. It tells us the order of terms. So usually we'll begin with n equals 1. Sometimes we can begin with n equals 0. There will be cases later on in this chapter where we will have to be careful about which one we're starting with, and we'll kind of pick the same one here. So looking at an example here, we've got a sequence 1, 4, 7, 10, 13, 16, and we've got two different ways we can write this one. First, if we look at this, we see that each term can be gotten by taking the one before it and adding 3. So we got that here. A sub 2 is a sub 1 plus 3, a sub 3 is a sub 2 plus 3, and so on. So we've got this situation. We got a sub 1 equals 1, that's our start, and each term is the term before it plus 3. This is a recurrence relation or an implicit formula. So we call it an implicit formula. It's also called a recurrence relation because it kind of feedbacks into itself over and over. It specifies the initial term and gives a rule for the next term. So if we want a sub 147, this is going to be miserable to do. We'll have to find each and every term all the way up through 146, then add 3 to it to get 147. So it would be much nicer to get an explicit formula out of this. And so what we'll do is we'll go ahead and figure out then, based off this guy and based off our general rule here, we've got a sub 1 equals 1. We'll try to figure out a general formula. A sub 2 is 1 plus 3. A sub 3 is 1 plus 3 again. A sub 4 is 1 plus 3 plus 3 plus 3 once more. And we can keep going until we're confident that we have a good pattern here. All right, so in any case, we have 1 plus a number of 3's all added together. So we can turn this into some sort of multiple. And so we want to figure out what is that multiple. It's going to be dependent on n, the index. Well, we've got 4 3's here. 3 3's here, 2 here, 1 here. And that actually means up here we have 1 plus 3 times 0. And so we notice that the relationship between the index and this number we're multiplying by is that if we were to go on to a sub n, this would be 1 plus 3 times n minus 1. The number of 3's we add is always 1 less than the index. And so here's our general formula then. And so a sub n would be equal to 1 plus 3 to the, times n minus 1. We could also multiply this out. 1 plus 3n minus 3. And so when we add these together, we get 3n minus 2. And that's what we have here. The nth term is determined by a sub n equals 3n minus 2 for natural numbers n. This is an explicit formula, so we can get the nth term just by plugging in n. So a sub 147 is going to be 3 times 147 minus 2. So we multiply that out. 21. Let's see, 3 times 4, then plus 2, and finally 441. So we get 441 minus 2, so we get 439. And that way we're able to find a sub 147 without having to go through each and every term. So this is sometimes possible. It'll be possible in a very strict set of circumstances. This is one of them, whenever we are adding a specific number to get to the next term. Right, so we'll look at another case here. This one is an explicit formula, and we want to write the first 4 terms. So to find a sub 1, we plug in n equals 1. And when we do that, we get negative 1 times 1 over 1 plus 1. So we get negative 1 over 2. A sub 2, we got negative 1 squared times 2 over 2 squared plus 1. So we get positive 1 times 2. And then on the bottom we get 4 plus 1. So we get 2 fifths. A sub 3, we plug in 3. Negative 1 to the third times 3 over 3 squared plus 1. We get negative 3 over 9 plus 1. That's negative 3 tenths. And then a sub 4, negative 1 to the fourth times 4 over 4 squared plus 1. We get positive 1 times 4 over 16 plus 1. So we get 4 over 17. So our first 4 terms, negative 1/2, 2 fifths, negative 3 tenths, 4 over 17. So we notice, what does the negative 1 to the n do to the terms? Negative, positive, negative, positive. The signs alternate. Based off this negative 1 to the n. And that's something that's going to pop up a lot throughout the chapter. A negative 1 to the n will alternate our signs. All right, so we have another sequence here. We want to find the next 2 terms, a recurrence relation, and an explicit formula. So first off, we have to figure out what's happening to get to each term. So we're adding 3, then we're adding 6, then we're adding 12, then we're adding 24. It looks like it'd be better if we just multiplied by 2 each time. So it looks like to get to the next, we'd be multiplying by 2. So we'll multiply 48 by 2, we get 96. Multiply 96 by 2, and we get 192. And so those are our next 2 terms. The recurrence relation then is that b sub n is going to be b sub n minus 1, the term before it, times 2. And we have to figure out where do we start. Our first term here should be, we actually have to write the first term. B sub 1 equals 3. For n equals, we want 3 to be the first thing we plug in here, so we're looking at plugging in 2 for n. And so on. So that's our recurrence relation. The last thing we do then is find our explicit formula. So in this case, we've got b sub 1 equals 3. B sub 2 is 3 times 2. B sub 3 is 3 times 2 times 2. B sub 4 is 3 times 2 times 2 times 2. And we do the same sort of process then. Oops, b sub n. We've got 3 times 2 to the third, 3 times 2 squared, 3 times 2 to the first, and 3 times 2 to the 0. So it looks like we're always going to have 3 times 2 to the relationship here is, again, the power on 2 is 1 less than the index. So b sub n will be 3 times 2 to the n minus 1. Right. As it says here, perhaps the most important question, if you go farther and farther out in the sequence, all the way out as far as we can, what happens to the terms of the sequence? Do they approach a specific number? What is the number? Do they grow without bound? Do they wander without pattern? Do they oscillate? Do they sort of find 2 different values that they attach to? We will talk about this long-term behavior, talking about the limit. And when limits were first discussed, this is actually where the discussion began. So you've worked with limits definitely in terms of functions where we have an x affecting a y, but figuring out where a sequence goes is the first place that we really talk about limits, mathematically speaking. So the terms of a sequence approach a unique number L, then that means that this limit exists. The limit as n approaches infinity of a sub n. That means that the sequence converges to L. Very important. Again, we talked about this when we were talking about our improper integrals. Convergence and divergence are going to be huge in this chapter. If the terms do not approach a single number, that means if they approach multiple numbers, if they go to infinity, negative infinity, if they oscillate, if they wander around, the sequence has no limit, the sequence diverges. Limits of sequences are really no different from limits at infinity, except we are talking about n, and it's only integer values. So how can we figure out, based on what we know from functions, how can we move it into this realm of only integer values? We have a theorem for that. So we have f is a function with f of n equal a sub n for all positive integers. That's our sequence. If we are looking at a function instead over the real numbers, and we're approaching some limit, then the sequence is also approaching that limit. So sometimes we'll convert to a function. We're really just going to sort of use this to say skip over that. We're just going to let the limit go to infinity. And so we're essentially going to treat this situation the same as we would for a function. We're just by using this theorem. All right. So we have then our first of our many properties theorems. We're going to have several of those this semester. If we have 2 sequences, a sub n approaching a, b sub n approaching b, then we have these situations. We have additivity. If we're adding or subtracting the sequences themselves, we can add or subtract the limits. We have constant multiple rule. If we have a constant multiple multiplied by each of the terms, then we can actually take that, take the constant multiple out, apply the limit, and then multiply it back in. And that's for any real number. We have multiplication here. If we multiply the 2 terms sort of pairwise, a1 times b1, a2 times b2, a3 times b3, all the way up here, then we actually do get the product of the limits themselves. And the same thing for division. And again, that's provided that we're not dividing by 0. Right? We'll talk about growth rates as well. That's going to be important, especially in this kind of case. We've talked about, well, you should have talked about, rather, growth rates in Calc 1, specifically talking about limits going to infinity there, and L'Hopital's rule. So we have a similar kind of thing going on here. If we have something that's growing faster on the bottom of our limit, then the limit will go to 0. All right, so this is going to be in order here. We're going to have the slowest growers on the left, the fastest on the right. And the symbol we should be using for growth rates is this double less than sign. And here, as it says down there, P, Q, R, and S are positive real numbers, b is a positive real number, and it's greater than 1 as well. So we are going to need to be able to work with this, get to this point first before we can apply this theorem. So the slowest growing thing is a natural logarithm or some sort of logarithm, even to a power. After that, we have, when we have maybe a polynomial type of thing going on. Faster than that is a polynomial times a logarithm. Faster still than that is when we have just a higher powered polynomial than if we had it over here. Higher than that is an exponential if our n is in the exponent. More than that, we have the factorial, which we are going to be working a lot more with this semester than you probably did in calculus. And at the very most, we have the tower function. And that's going to be our greatest growth rate there. So we are going to have to revisit L'Hopital's rule. We're going to be using that a lot here. So remember that the only times that you can actually use L'Hopital's rule are right here. In all of these other cases, there's some sort of modification that has to occur to be able to get into one of these forms. This is the only time, again, that we can use L'Hopital's. For all of these other ones, we must convert to one of those other forms. That should be OR. And then use L'Hopital's. So, do the following series converge or diverge? That is simply asking for the limit as n tends to infinity of this entire thing here. 8n squared plus 800n plus 5,000 over 2n squared minus 1,000n plus 2. And so remember that the way that we're going to deal with this is by multiplying 1 over, for the top and the bottom, the largest power of n in the bottom. And so when we do that, we get 8n squared over n squared plus 800 n over n squared plus 5,000 times 1 over n squared. In the denominator, 2 times n squared over n squared minus 1,000 times n over n squared plus 2 times 1 over n squared. And remember that when we are writing our limits, they do need to appear in every line. We do need to write limit as n tends to infinity on every line until we've actually finished evaluating. Right, so we look here, we get 1 and 1. In this particular region, again, we get using the growth rates argument or probably a theorem that you learned in Calc 1. We have 1 over n, which goes to 0. So this whole thing goes to 0. So this whole thing goes to 0. This whole thing goes to 0. And finally, this one goes to 0 as well. And so we have evaluated our limit. It's at 8 over 2. So we get 4. So this series converges. We have achieved just a value here. We weren't asked what the value was. We were just asked whether it converges or diverges. For this next one, same question. The limit as n tends to infinity, does this go somewhere? Right, and for this one, we can evaluate. We've got 3 over n. This guy goes to 0. So we're looking at 2 to the 0, which is 1. So this guy converges as well. Right, you always want to start by trying to plug in your n and see if there's something simple that you can work with. Watch out for these indeterminate forms here. If you plug in and find one of those to be the case, then we'll actually have to work with it. But we don't want to assume that we have an indeterminate form automatically here. when we get down to this one, 5 plus n over n all to the nth power. And we think about what happens if we plug in infinity. Well, right, these guys will have the similar growth rate. We got 1 to the infinity. Okay, so that's right here. We don't know, is the inside going to be approaching 1 faster than the exponent is going to be approaching infinity, or is the exponent going to approach infinity faster than this guy approaches 1? In one case, we'll get something like 1. In another case, we will get infinity. Depending on how fast one grows over the other, we could get all kinds of different values. So we'll have to go ahead and calculate this limit using something that we might remember from Calc 1. We let y equal 5 plus n over n to the n. We take the natural log of both sides. And what this does is this allows us to take this exponent and bring it out front. And so what we'll do at this point is we'll go ahead and apply the limit as n tends to infinity. And we don't necessarily have to keep writing the left side anymore as long as we put an equal sign over there. And so now we evaluate this limit. We got infinity here, and we've got natural log of 1 is 0. And so we're at this case instead, 0 times infinity. And this one is just one step away from being one of these guys. All we have to do is take our n and somehow send it to the denominator. And we do that by writing that it's 1 over n. This is now 0 over 0, which is something that we can use L'Hopital's rule on. We have one more thing that we should probably do to just kind of clean up a little bit before we do that. It'll make our derivative a little easier. So let's go ahead and split this fraction up on the inside there. We've got 5 over n plus n over n, which is going to give us 1. And now that'll be much easier to work with. So we'll go ahead and apply L'Hopital's rule. So in the denominator, power rule, this is n to the negative first. So negative n to the negative second. In the numerator, we've got the argument sent to the bottom, 5n to the negative first plus 1. And then the derivative of the argument in the top, negative 5n to the negative second. All right. And so we've got some nice kind of cancellation that can happen here. We've got, if we maybe rearrange a little bit, negative 5n to the negative second, negative n to the negative second times our denominator here. And so the negatives cancel, the n to the negative seconds cancel. So we get the limit as n tends to infinity of 5 over n plus 1. Now we can apply this limit. This guy goes to 0, so we got 5. So the limit as n tends to infinity of the natural log of y is 5. And so we take the exponential of both sides, we get e to the 5th. And so that's going to be this limit here. And so this guy converges. So we do have to pull back in our minds and remember how this really works in terms of L'Hopital's rule. We do have to remember how that works. All right, next thing we're going to do, figure out the two behaviors here. We've got two different sequences, one involving natural logarithms, and then down there we'll go ahead and look at the roots as well. So we've got the natural logarithm, right? And if we just sort of start to evaluate our limit here, as n tends to infinity, a natural log of n minus natural log of n plus 1, we'll go ahead and get natural log of infinity minus natural log of infinity. So we'll get infinity minus infinity, which is no good. Fortunately for us, we have log laws. If we have subtraction in between two logarithms, we can actually turn this into division in a single logarithm. At this point, then, we can go ahead and work on the inside here. We've got another polynomial, rational, it's two polynomials. We'll go ahead and multiply by 1 over the highest power in the denominator, which is n to the first. When we do that, we get natural log of 1 over 1 plus 1 over n. This guy goes to 0. So we get natural log of 1. This whole thing becomes 0. So this guy converges as well. Right, so again, it's kind of one of those cases where we really do have to remember in Calc 1, I know it's maybe been a while since we've done stuff with L'Hopital's rule, but we are going to have to be careful to acknowledge how this stuff should work. Be very careful. Since it has been a while, there's probably some off-limit stuff that we might have forgotten, especially when it comes to dealing with these square roots. So if we were to take the limit here, then we very definitely get infinity plus infinity under a square root minus infinity, right? So for sure an indeterminate form. So we have to figure out how can we kind of angle this, how can we kind of convert it back into one of these forms, either 0 over 0 or infinity over infinity. So to do that, we're going to have to introduce a fraction. And our favorite way to introduce a fraction when it comes to dealing with roots is to multiply by the conjugate. And when we do that, right, some nice stuff happens. We've got the limit as n tends to infinity of, we end up with the difference of squares in the numerator here, so n squared plus n minus n squared over root n squared plus n plus n. Sorry, plus n. And so in the numerator here, there's some cancellation that happens. We just get n over this root. All right, so in this case, we do end up with infinity over infinity, right? That is something that we could use L'Hopital's rule on, because this is very clearly infinity. Now everything's positive. But we don't necessarily have to. Usually dealing with derivatives when it comes to roots is a little more difficult than we would like. So we'll go ahead and use the same strategy we had been doing for all of these rational functions. That is multiplying by the greatest power that we see in the denominator. And it looks like we have n squared under a square root. So we're looking at multiplying both the top and the bottom by root n squared, which is just n. When we do that, we'll get 1 in the top, 1 there. Let's see, we've got n squared plus n over n. So we're going to have to figure out how do we get the n into that root. Well, we can do it by making it into an n squared. Now it's under the root. So we split the fraction inside that root. N squared over n squared plus n over n squared. And so we'll get the limit as n tends to infinity of 1 over root 1 plus 1 over n plus 1. This guy goes to 0. So we get root 1 plus 1. That's 2 in the bottom and 1 on the top, so 1/2. So this guy converges. And in fact, it converges to 1/2. We can state that as well, converges to 0. Back up here. Since we weren't just asked to figure out does it converge or diverge, we were asked to determine the behavior. the behavior does mean if it converges, what does it converge to? So we've got both of those there. So we'll talk about some specific types of sequences from here. So firstly, if we have a sequence where each term is greater than or equal to its preceding term, it's non-decreasing. So our terms either stay flat or they go up. They can flatten, go up, that kind of thing. Just, it's never going to go down. On the other hand, a sequence in which each term is less than or equal to its predecessor is non-increasing. So it can either stay flat, it can continue to go down, flat, down, something like that, as long as it never goes up. Any sequence that is either non-increasing or non-decreasing is monotonic. So monotonic, right, the Greek prefix mono, meaning one, and then the tonic being the tone, the direction. It's the progression. It's the progression in only one direction. And so that's going to be an essential piece we need for a theorem coming up here. The last thing we need is being bounded. So a sequence is bounded from above if there is a number m that acts as a ceiling. So that all of our terms here, I'll go ahead and start making terms as dots, since these should be integers going in here, 1, 2, 3, and so on. We should just have dots. It shouldn't be smooth continuous lines. If there is some ceiling for all of our n here, m is the upper bound, and m could be up here, even though all of our terms stop here. There's a bunch of upper bounds possible. If we have one, we have an infinite number of them. If m is an upper bound for a sub n, but no number less than m is an upper bound, then m is the least upper bound. So if we can get exactly the ceiling of our sequence, and it maybe even is almost an asymptotic behavior, then m would be the least upper bound. As soon as we try to bring this particular line lower, we start running into points here. This is also known as a supremum. And it's a really important analysis term, a supremum. There's a similar idea for being bounded from below, and it's if there's a floor. And there's likewise a greatest lower bound. And that's going to be called an infimum. It's got a similar importance to the supremum. But regardless, the monotonic and the bounded are the two pieces that we need for the monotonic convergence theorem. A bounded monotonic sequence converges. So the idea is, if we always have to go either up or stay flat, and there's a ceiling, then the ceiling is usually going to be our stopping point or our limit, right? If we've gone this high, we can never go back down, and we can never break through the ceiling. So it has to be some sort of limit for us. And likewise, the same thing for a floor, for a non-increasing. So how do we know if the terms of a sequence are non-decreasing or non-increasing? The way that we have to do it is by comparison. So we'll compare a sub n and a sub n plus 1. All right. So we'll go ahead and look at b sub n. It says determine the behavior. So we're either determining that it diverges or if it converges, what it converges to. So we see this guy here, this -1 to the n. So this causes oscillation, which means we have to look at the two different cases. If n is odd, and if n is even. So if n is odd, then our limit as n tends to infinity of b sub n is going to have a negative there, negative n to the 3 halves over n to the 3 halves plus 1. And we'll go ahead and use the same strategy. I forgot my limit, which is a big no-no. There we go. We'll employ the same strategy as before. We'll multiply the top and the bottom by n to the largest power in the denominator, which is 3 halves. So we get negative 1 over 1 plus 1 over n to the 3 halves. This guy goes to 0, so we get negative 1. On the other hand, if n is even, then the limit as n tends to infinity of b sub n will be the limit as n tends to infinity of, now we have a positive here, n to the 3 halves over n to the 3 halves plus 1. Same strategy we employ here. And we get a similar result, although not the same. We get a positive 1. And so our result would be positive 1. So we get two different values. We look at sort of half of our sequence is converging to one value. The other half is converging to another value. And so they're acting as opposition here. We're sort of going to get some values that go up to 1. And in the meantime, we'll get opposing values where all the gaps are here. We'll get opposing values that go down to negative 1. And so if we're looking at our sequence, it does not converge. And so the reason for that is if we look at the overall limit of b sub n, and we say, what should this limit be equal to? Here's how we'll phrase the answer. The limit does not exist, and therefore b sub n diverges. So we'll go ahead and stick that in. B sub n diverges. And so on this chapter, especially, we're going to want to work on phrasing our answer in a logically derived kind of way. This whole thing would have to be considered part of the answer then. We're going to end up having multiple different tests that we'll use to test convergence or divergence later on, and we'll have to state which test we used on which sequence and what the result is as our answer. All right, so next thing we look at here is a specific type of sequence, the geometric sequence. So the geometric sequence, as it says here, they have the property that each term is obtained by multiplying the previous term by a fixed constant called the ratio, and that gives us r. And so they have the form r to the n, where the ratio is a real number. So we've seen something kind of like this before. We dealt with one back a little bit ago that looked like 3 times 2 to the n minus 1. It's sort of a modified geometric sequence. But if we look at a geometric sequence, we will have a nice tidy theorem for when it converges. So if our common ratio is going to be less than 1 or greater than negative 1, right? So r is between negative 1 and 1. Then our terms will get smaller and smaller and smaller, and they'll go down to 0. If r is equal to 1, we'll have 1 times to the nth power. As n gets bigger, we just get more 1s. So we'll end up at 1. If r is bigger than 1, so if in magnitude, so if r is greater than 1 or r is less than negative 1, what's going to happen is as we put a bigger and bigger power, our terms are going to explode either toward positive infinity or negative infinity, and so our limit won't exist. If r is greater than 0, then r to the n converges or diverges monotonically. If r is less than 0, then it's going to happen by oscillation, because if we have a negative number here, odd powers will keep it negative, and even powers will make it positive. So we apply that theorem. Do the sequences converge or diverge? If it converges monotonically or by oscillation. And so for all of these, it's simply going to be a matter of looking at R. So R equals, in this case, 1.2, which in this case is going to be, if we look at the absolute value of R, that's the absolute value of 1.2, greater than the absolute value of 1. And so in this case, this guy is going to diverge. So the limit of 1.2 to the n here does not exist by that previous theorem, and therefore 1.2 to the n diverges. All right, so that's our basic setup here. This guy doesn't necessarily look like r to the n, so we're going to have to do a little bit of modification first. We've got 2 to the n times 1 over 5 to the n. Now they at least have the same power. That actually means that we can smash them together. So we've got 2 to the n turns into, 2 to the n times 1/5 to the n turns into 2 times 1/5 to the n. That's 2/5 to the n. And so now we have our r here. R is going to be equal to 2/5. Absolute value of r is the absolute value of 2/5, which is 2/5, which is less than 1, which means that this guy is going to converge. If we look at the limit then, as n tends to infinity, of our original sequence here, 2 to the n, 5 to the negative n, that's going to be same as the limit as n tends to infinity of 2/5 to the n, which will, since our r is less than 1, go to 0. And therefore, our sequence will converge. So it converges to 0. And we have to determine which way it happens. Our r here was positive, so this is going to be monotonically. And so that's our answer. Our next guy here, our r here is -2. Absolute value of r is the absolute value of -2, which is 2, and that's greater than 1. Which means that the limit as n tends to infinity of this guy does not exist. And since that does not exist, therefore, our sequence here diverges. All right, last one. R is going to be equal to -0.92. Absolute value of r is absolute value of -0.92, which is 0.92, and that's less than 1, which means that if we look at our limit as n tends to infinity, we're going to approach 0 based on that theorem that we've looked at, and therefore the sequence converges to 0 by oscillation, because our r here is negative. So geometric series are very nice to deal with. Kind of the most complicated they can get is if we kind of split up parts into different exponents here. So the next thing we'll look at here is the squeeze theorem. This is the last thing we'll look at for this particular section. If we have 3 sequences, and we have that sort of one term is always squeezed between the other two, this is true for each n. So a sub 1, c sub 1, squeeze in b sub 1. A sub 2, c sub 2, squeeze in b sub 2. Right? This has to be true sort of n-wise. But it only has to happen greater than some index n. Because in a sequence, there's a sense that we only really care about what's happening sort of on the what we call the tail, or what happens closer to infinity than not. So we could have all kinds of random behavior happening for the first couple terms, but we need all this to line up greater than n forever. So if we have that the smaller sequence converges to L and the bigger sequence converges to L, then the one in the middle has to converge to L also. It's very similar to the squeeze theorem for functions. It behaves almost the same way. So we'll go ahead and take a look at an example here. We'll find the limit of this sequence. So often what will happen for a squeeze theorem problem, what will happen, in fact, most of the time, is we'll have an oscillating trig function, and that's going to be our basis for setting up our inequality. We need to set up this inequality here, where our b sub n is in between two other values. And for cosine, we have a very clear distinction. We've got -1 less than or equal to the cosine of n less than or equal to 1 for all real numbers. And so that'll be true for all natural numbers as well, because the natural numbers are a subset of real numbers. If we have a real number, then what we want to do is we want to start working toward getting the middle to look like this guy. So we need to specifically look at dividing by n squared plus 1. The problem is if we divide in an inequality, sometimes we have to flip the signs, right? We want to ensure that dividing by n squared plus 1 does not flip sides. So n squared plus 1 is always going to be positive. So acknowledging that, we have our solution here. Dividing by n squared plus 1 does not change the direction of inequality. So we don't have to switch our signs rather. And so we establish that. So we can go ahead and divide. We say the result is, we've got -1 over n squared plus 1 less than or equal to cosine of n over n squared plus 1 less than or equal to 1 over n squared plus 1. So we have our inequality established, and it's for all real numbers, in fact. So certainly for all n, and then certainly for all n greater than some index. So we just have to establish this part now, that both of these limits on the outside are the same. So we'll go ahead and apply the limit to all three spaces in our inequality. And when we do that, we're hoping to get the same limits on both sides. And so we wrap up our limit here. And when we do that, we get that the first limit here, this guy goes to 0. And when we look at the last one here, this guy also goes to 0. So looking at our squeeze theorem, we've gotten this, so that means we must have this. So that means that the limit, we can say therefore, since this is the conclusion of our theorem, the limit as n tends to infinity of the cosine of n over n squared plus 1 equals 0, and that's going to be by the squeeze theorem. And therefore, b sub n converges to 0 by the squeeze theorem. All right, so to recap, a sequence can converge to a single value. That's the limit. It can increase in magnitude without bound, so to infinity or negative infinity, might bounce back and forth between them. It diverges then in that case. The terms may settle to an oscillating pattern in which we're approaching 2 or maybe even more values, but that still diverges. They may stay bounded even, but just wander forever without a pattern. That will diverge also. And so that will be kind of our basis, this idea of sequences. We'll go ahead and start from that point, and we'll build up into something even bigger and better in the next section.